In this video, I want to look further into the integration of hyperbolic functions. When you're dealing with hyperbolic functions, you have a choice between using techniques which you have used with trigonometric functions and using exponentials. Let's look first at the integral of tan to the 5x sec squared x dx. Just a moment's thought should convince you that you don't really want to put exponentials into that, particularly when you think that it looks like the integral of u to the 5 du by dx. So let's use that idea and differentiate u to the 6, which is tan to the 6. That gives us minus 6 tan to the 5 x sec squared x, and so our integral I is just equal to minus 1 over 6 tan to the 6x plus c. Nice simple integral. What happens now if we look at the integral of cos x over 1 plus 3 sin x dx? You could turn that into exponentials. You'd have an e to the x plus e to the minus x on top, 1 plus 3 over 2 e to the x minus e to the minus x on the bottom, beginning to look a little bit complicated. And you see something else which will help us there. It does have the form of the integral of 1 over u du by dx, if we ignore numbers. And so if we differentiate log u, which is log 1 plus 3 sin x, we get 1 over 1 plus 3 sin x times, differentiate the bottom, 3 cos x. And this tells us that our integral is equal to 1 over 3 log 1 plus 3 sin x plus c. Moving on. Integral of x sin x. Exponentials, integrating x e to the x and x e to the minus x. Two lots of integrating by parts, whereas if we think of x sin x, we're only integrating by parts once. So let's go straight into integrating by parts. We start with u equals x, u dashed is 1, v dashed is sin x, v is cos x. This is now going to be the integral. Well, before we get to integral, uv, which is x cos x, minus the integral of v, which is cos x, times du by dx, which is 1 dx, which is x cos x minus sin x plus c. Quite straightforward using our trig techniques. Here we have another one, which if we were faced with trigonometry, we would do that by parts. But if you look at the exponential form of that, let's try that. We get the integral. Cos x is a half e to the x plus e to the minus x dx. And so that is equal to, let's take the half out, integral of e to the 3x plus e to the x. Integrating e to the 3x, I get 1 over 3 times 2 e to the 3x. Integrating e to the x, I get e to the x times a half plus c. So that was very simple when we decided to use the exponential form. What happens here? If I put the exponential form in, it could be done. It's e to the x minus e to the minus x cubed, which is just a binomial expansion, and integrate each term. So it's not too difficult. Or we could think along the lines of how we would integrate if it was sine cubed. I would rewrite this first as sine squared x times sine x. Sine squared, if we remember that cos squared x minus sine squared x is 1, then sine squared x is cos squared x minus 1. Times sine x dx. I've now got the integral of cos squared x sine x, which by now you should look at as something nice and easy, minus sine x dx. Integrating cos squared sine must have come from cos cubed. Differentiate cos cubed, 3 cos squared sine, so I get 1 over 3. Integrate sine, I get cos plus c. Now let's look at the integral of sec x. If we compare that with the integral of sec x, the trick here was to multiply top and bottom by sec x plus tan x. Sec x plus tan x dx. That trick enabled us to look at the denominator. If I differentiate sec x, I get sec x tan x. Differentiate tan x, I get sec squared x. So this is 1 over u du by dx. It's a straightforward log integral. So that equals the natural log of sec x plus tan x plus c. Unfortunately, if we play the same trick, if you put h's on the end of this, it goes wrong, because when you differentiate sec, you get minus sec tan, so that the same technique just doesn't begin to start. What happens if we move over to using exponentials? This is the integral of 1 over cos x dx. Cos x is a half, which gives us 2 on the top, e to the x plus e to the minus x. Multiply top and bottom by e to the x. It is possible to spot that by reverse chain, but just a little bit tricky. So let's use a substitution. Let's put u equal to e to the x. In that case, du is equal to e to the x dx. And e to the 2x is u squared, so that's the integral of 2 over u squared plus 1, e to the x dx is du. That is now a standard integral. So that's 2 arc tan u plus c. Put it back into x's is 2 arc tan e to the x plus c.